in this homework. So here's one of the questions that you saw addressed in the video that you watched. What's the minimum speed at which we can spin a cup of water in a vertical circle so that it stays in the cup when it's upside down? And since we're here, why not do it? Here's my cup so you can see the water in it. I won't fill it up too much, so hopefully I don't mess it up. And maybe I should unshare. Oh, this is not good. This cup is getting a crack in it. Well, hopefully we'll make it through without having a disaster here. I think I need to get a new cup. It's getting a crack in it, but it doesn't seem to be leaking much. I don't know if Hamangi can see this or not, but in any case, you kind of have an intuitive sense of how fast you have to swing this so that it makes it all the way around without the water coming out of it. And certainly if you swing it really fast, there's no problem. But everybody has the sense that if you don't go quite fast enough, that water is going to stall out at the top and the water will fall out and the cup, essentially this string will become slack. It won't be taut anymore. And so the question we want to address now is, what is that minimum speed? Okay. It's, excuse me, similar to this problem of a Hot Wheels car or some sort of, toy car going around on a vertical loop of a track. We're going to assume since we're talking about circular motion, we'll assume that the loop is perfectly circular of radius r. So if this car is going around this loop, what does its speed have to be here? It's not going to have any problems down here with the speed being too small, but when it's upside down, if it's not going fast enough, if you ever played with these when you're a kid, it goes up and then it falls off the track before it gets to the top. And so that's a similar kind of thing. Instead of the water falling out of the cup, we have the car falling off the track there. And I said in the video, I think there's a video you can see on the web of this person doing this, and it was a rather dramatic thing to actually drive a car in a loop because the forces involved are so big that you can actually pass out the same way, a fighter pilot, if you pull too many G's, as people say, if your acceleration is too great, all the blood drains from your head and you can pass out. And so they were concerned, not at the top, but when you're starting to go up here, that the forces would be too big, and so they had to go fast enough, but you can't go too fast or those forces get really huge. And there was a small range of speeds, according to the video that I watched when I just looked it up, that would make it work. So here's how to think about it. We're going to think of a free body diagram of the object as it's passing the top. So that's just shown in red up here. We're imagining it's going with some big speed v. If this thing is going around with a big speed v, it's going to be whipped around. It's going to feel like it's smashed towards the top. We'll talk about where that comes from a little bit later on, but you have that intuitive sense that it's being mashed against the top. The track is pushing down on that car quite a bit if it's going really fast. Here's the reasoning why in terms of Newton's second law. The free body diagram looks like this. The car, of course, has its weight force, so we'll assume it has mass m. There's mg going down. If it's going really fast around a circle, we know from our v squared over r formula that the centripetal acceleration is going to be really big, right? R is what it is, but v is huge, we're assuming. So when you put that v squared in there, the acceleration is going to be huge, and so we need a huge net force to result in that acceleration, and maybe the weight isn't enough. So what makes up the difference? The track makes up the difference. It pushes down with a huge force to make just the right force to keep it going on a circle. As you start to slow it down, so here notice I'm changing the vector. That's a very fast speed. Here's a somewhat fast speed. R is the same, but V's gotten less. And so the V squared over R has gotten less. This is less. That means we don't need as big of a net force. Now, mg isn't at liberty to change. It is what it is because the mass has whatever car it has, whatever mass that the car has. So the only thing that can change is the downward force from the track, and it gets smaller. And as we decrease the speed at which it's going around, the required acceleration, or that v squared over r acceleration for staying on the circle, gets smaller. The force from the track gets smaller. At some critical speed, just the weight of the car by itself is just the right force to give the acceleration that's going at that minimum speed. And if we tried to go at an even smaller speed, the acceleration vector would get smaller still. And then the weight force would be too big. And the only way for it to be subtracted off of is if the track pushes up on the car. Now, in the normal way we have Hot Wheels tracks, they aren't stuck on there with some rails or something. There's no way for the track to pull up on the car. It can only push down on the car. And so at that point, before it gets to the top, the car would leave the track and it wouldn't be on a circular thing anymore. So in any case, that critical speed, what's the slowest speed that it can round the top at, is given by when mg is just the right, the weight force is just the right force needed for the acceleration at that speed, right, using F net equals ma. So we're just going to set F net equal x equals max. Since we're at the top here and the direction towards the center of the circle is down, let's choose down to be the plus x direction. And there's only one force, right? There were two forces, but now the track force has gone to 0. So the left-hand side is just mg, and the right-hand side we have ma. That's m times v squared over r. We'll interpret that as the minimum v. And when you cancel out those two m's and then solve for v, you'll get root g times r. So that's kind of an interesting result. And according to this, we're supposed to look at problem 1 on here. Okay, I wasn't recognizing this for a second, but now, yes, I do. Okay, forgotten what order I put things in. Here, a person swinging a 0.1 kilogram mass on a light string in a vertical circle, radius given 40 centimeters. Where's my mass? Here it is. So a vertical circle means it's going up and down with respect to Earth. Okay, so I'm swinging this in a vertical circle. If the mass passes the top at a certain speed, what's the tension in the string? If the mass passes the top at a different speed, what's the required tension in the string? And a similar question about the bottom and the side. So see if you can, the idea is at those three positions, it's sort of similar to what we did with the Ferris wheel, and in fact simpler. In this case, instead of a force from the track like we had back here, we're going to have an additional tension force. The tension's playing the same role as the track. It's giving that additional force that can adjust as you change the speed. So try doing problem 1, all 4 parts. And we'll come back together and discuss it.
Dr. Kelly, I can't see the board. Could you move the camera a little to the left?
Sure.
Thank you.
So you can see it, you just can't see where I'm writing. Maybe I need to check where it's zoomed in. Is it okay if I pull out a little bit like this? Can you see it now?
Can you shift it a little towards the left?
I see, it's not aimed straight ahead.
Mm-hmm. Thank you.
Can you see the two edges of that piece of board?
Yes.
Let me go look. Yeah. I was trying to make it big enough for you to see, but maybe that makes it so we can't see the edges. Anyone having trouble getting started? The stuff we did in chapter 4 is key. You want to start with a free body diagram at the moment we're concerned with. So in part A, that's at the top when it's swinging over the top. What are all the forces on it? Choose relevant axes and then do F net equals MA. Put my answers up here. Okay, let's come back together and work on them together. So the idea is in this case, because the free body diagram is not too complicated, I could draw it to the side, but I'm just going to turn my sketch into a free body diagram for this. Here's my 0.1 kilogram mass, and it's going around in a circle there. Its mass is 0.1 times, its weight is 0.1 times 9.8. That's one force that's on it. And if the string is tugging down on it at that instant, there's some tension T acting as well. And I think those are the only two forces I can think of. So let's, as usual, take plus x to be toward the center of the circle, because we're going to use our v squared over r acceleration. So for A, sum of the force x components equals max. Let's fill that in. Both of these come in with plus signs there. So I have t plus 0.1 times 9.8. And that's equal to the mass of the thing in the free body diagram times the resulting acceleration, and that's v squared over r, and our v in this one is 3, if I remember correctly. Yeah. 3 squared over r, and r is 0.4 meters. Okay, so that allows me to calculate t, and I get 1.27 newtons. So that's A. And then in B, we're really asked the same thing, only the speed has changed. So let's see what happens. I can use the same free body diagram in B, but the only difference is that this 3 meters per second changes to a 1. So I get t plus 0.1 times 9.8 is equal to 0.1 times 1 squared over 0.4. And that, when I calculate it, gives me a negative value for t. T equals minus 0.73 newtons. Now, what do we make of that negative t? Well, I guess the usual way that t would point is like this. And so t is supposed to be the length of this vector. If I guess a direction for t and the required t ends up, when I solve for it, being negative, what that means is we're talking about a vector pointing in exactly the opposite direction from which we guessed. And we'll see that we use this technique sometimes when we don't know the direction of a vector. The point is, what that means is that the tension force would have to actually point up on the mass, and a string is incapable of doing that. It would be fine if it were a rigid rod or something. It could hold the mass up as it went over the top. But you can imagine if this is going really slowly, a rigid rod would have no problem pushing it up over the top, but a string just can't do that. So it falls off the circle before it ever gets to that point. It falls off when the required tension becomes 0. That's when the string starts to become slack. Questions on B? All right, in C, we're supposed to do at the bottom. So here we have our 0.1 kilogram mass. Still, of course, the weight force is downward, but now the tension force is upward. I'm going to take plus x toward the center of the circle, because why not? That'll make my acceleration positive. And then sum of the force x components equals max. Same formula we're starting with. T comes in with a plus sign. This comes in with a minus sign, minus 0.1 times 9.8. And that's equal to the mass in the free body diagram times v squared over r. And I believe in C, again, it's 1 meter per second. And notice in this case, compared to the previous one, the only thing that's different is the sign outside the 0.1 times 9.8. It's switched, and that makes all the difference, because instead of this as coming over here with a minus sign, it comes in with a plus. And a perfectly reasonable t is required. Over on the right, I say 1.23 newtons when you plug that into your calculator. Okay? And just to be sure, let's do it at the side, too. That's what D was. We still have the weight force going down, 0.1 times 9.8. Now, the only direction the string can pull is to the left if it's over on the right, halfway up. And therefore, in D, well, as usual, I'm going to take plus x toward the center of the circle. This has 0x component, and the t comes in with a plus sign. So t is equal to 0.1. I think it's still going at 1 in part D. Is that right? Yep. 1 squared over 0.4. Okay, and that, again, that's a perfectly reasonable value. Any questions on that? Yes?
I did it all that way, but I was confused if you can make X positive and it's at the bottom, because like if you're looking at it overall, then T's pointing down that way and is positive, but when it's at the bottom, it's pointing up and is still positive. Does that matter?
It doesn't matter. You can always choose your axes any way you want them to be, and then you have to carefully think about each of the forces and what the signs of their components along that positive direction would be. So in this case, for example, you were talking about at the bottom. Suppose we had chosen oppositely. We kept the same convention we had at the top, okay? So let's go to the one at the bottom. I guess that was part C right here. What would have changed in there? Well, okay, so we're forgetting about this. T would have come in with a minus sign, so we're going to get a minus sign in this term right here. The weight would have changed signs as well, so I'm going to put a minus sign there just to indicate that it changes sign. And what about this side, the A? Does it change signs? Well, that would cause a problem because then we're actually going to get an overall minus sign. Well, we'll get something different than we had before, but it actually does change sign. What makes the MA part change signs when I switch my choice of plus X direction? Yeah, the acceleration is still toward the center of the circle. And notice that that's a negative X component in this new choice. So this one gets a minus sign too. This piece right here gets an extra minus sign. So everything in the equation changes sign, and that doesn't change the equation. That's just like you took the same equation and multiplied everything by -1. So algebraically, you should get the same answer. Other questions on that or comments? Different ways of doing it. It's, I almost always, when we're talking about circular motion, choose the positive direction towards the center of the circle because it's easy to forget the sign on that acceleration, right? You just sort of go into mindless mode and forget to put the minus sign on the acceleration. So I usually take it toward the center of the circle. Okay, so we've solved that. Let's look at a couple reading response questions here. Not from last night, but from the day before. Why would the driver of the car be more likely to pass out from too much acceleration at the top of the circle rather than while he's accelerating before entering the circular motion? Well, first of all, he's not most likely to, or whoever it is, I think it was a he that did it, was not more likely to pass out at the top of the circle, but rather when they first enter the circle and start curving. Because not only do you have your usual gravitational force pushing down on you, but now you need an additional force pushing up towards the center of the circle. So the most dangerous part is when you first start curving upwards. One of the other reasons I wanted to bring this up is that this was asking about while he is accelerating before entering the circular motion. So of course, to get up to whatever that critical speed is, that's just right to make it around, but you don't pass out, you have to accelerate, right? As presumably you're going straight and going faster and faster. That acceleration can take as long as you want. In other words, I could go with a really low acceleration for a very long distance, and that would get me to a large speed at the end. Or I could accelerate for a very small amount of time over a short distance and get up to speed really quickly. Now, if you did that fast enough, you might accelerate so fast that you would pass out from the resulting g-forces. But in this case, you can have a really long run up to it, and you can have a low acceleration. So that you're not limited on. But once you're on the circle, you've got to be going at a certain speed to make it around. And so you don't really have a choice. Once you're going a certain speed, that centripetal acceleration is determined by v squared over r. You got to have that minimum speed v when you're going around the top. Second one, in the free body diagram for the Hot Wheels problem, I don't understand how the car stays on the track if the net force, both of these things, the weight force and the track force, are pointing downwards. And yes, that seems somewhat strange. And I guess I have problem 2 on here because it's supposed to address that. Let's read problem 2. Person takes a cup. I won't do this because I probably wouldn't be able to do it, but person takes a cup containing 0.1 kilograms of water, and very quickly flips it upside down and shoves it down at 15 meters per second squared acceleration. And the question is about what happens when you're doing that. So just try that. This isn't a long problem, but answer questions A, B, and C. So we're concerned with the weight of the water. Well, that's just mg. I just wanted you to calculate it for comparison. How hard is the cup pushing down on the water? And I just kind of made up 15 meters per second squared. What's the minimum acceleration you could push it down with so that the water doesn't come out of the cup? You can kind of imagine that if I really shove it down fast, the water is not going to fall out of the cup. What's that minimum rate of acceleration so that it wouldn't fall out of the cup? And in this case, of course, we're not talking about uniform circular motion. Nothing's going in a circle here, so you can get out of v squared over r mode for a second. How many are finished with B? Okay, good. Let's just quickly do it. A is not supposed to be a mystery. You just do 0.1 times 9.8 is 0.98 newtons. But I just thought to compare that weight to the other force that's involved here, we're pushing it downward at 15 meters per second squared. So here's the water. I'm just going to draw it as a blob, 0.1 kilograms. It's got its weight force going down. And if I'm forcing it down, it seems like it would have a force from the cup going down too. Now, maybe I'm guessing wrong and the force from the cup has to be upward, in which case it can't really push in that direction. But let's see what happens here. And I think those are the only two forces, right? That's a contact force as well as an action at a distance kind of force. And since it's accelerating downward, why not take plus x downward and do the sum of the force x components equals max. That's F cup plus 0.98, that's 0.1 times 9.8, is equal to 0.1 times the acceleration, which is 15 in SI units. And when you put those numbers together, you get 0.52 newtons for F cup. So it's kind of like, I don't want to do it with the water to make a mess, but if I take this brass mass, right? Imagine this is water sitting in a cup, and it has something supporting it right now. And I take it and I flip it upside down, right? It doesn't lose contact with my hand as long as I'm accelerating downward until I sort of stopped accelerating toward the floor. And it's the same way with the water. What about the answer to C? 15 seemed good enough to keep the water in the cup, as long as you can keep accelerating it at that rate. What's the minimum acceleration? 9.8, right? Because that would mean essentially the water's in free fall and the cup's in free fall just right next to it. It's keeping up with it, so it's staying in the cup, I guess, barely. If the cup if we're being pushed down a little bit more, then it would actually be forcing the water to accelerate down. But they're both in free fall right next to each other. If I push it down, if I hold the cup and accelerate it down at 8 meters per second squared, the water is going to fall out and accelerate ahead of it at 9.8. Okay, so it's the same way with the loop. When the car is going around the loop, it's not as obvious, because we're talking about the acceleration when something's going in a circle. It's not as obvious that the acceleration is the same as when I'm pushing down, but it still is accelerating downward. So what's keeping that car on the track is actually the track pushing down on it. It's accelerating downward by a huge amount, and it's hard to see that in this picture, but the acceleration can be quite substantial, and its weight isn't big enough, so we need the additional track force downward to make up for it. All right, there was a section, very short section, and I didn't say much about it, but on non-uniform circular motion. And the idea there is, and I certainly didn't derive that this was the case, but it's a very similar situation in that when something is moving on a circle but at a non-constant rate, in addition to having a component of the acceleration that still points toward the center of the circle and it has the same formula as before, there's another component of the acceleration which points tangent to the circle. So I can think of maybe this object's going around in a circle, but at this point, in addition to staying on the circle, it's actually speeding up as it goes in that counterclockwise direction around the circle at the point that is shown here. That would mean that it has a centripetal acceleration towards the center of the circle, but that's just part of its acceleration vector. There's another component, the tangential acceleration, tangential component, which we would say points in this direction, along the tangential direction. And so its true acceleration would not be towards the center, but rather at some angle that's tilted forward along the direction of motion. So as it's moving, as it's speeding up, its acceleration vector, if I drew it with its tail where it was located, would not point directly in. That would be constant speed, but it would be tilted forward a little bit, somewhat along the direction of motion. But the component towards the center would still be the same. If it's slowing down, then if it's moving, down and to the left, its acceleration vector would be tilted back. And so part of its acceleration is opposite its velocity vector, and that means it's going to cause it to slow down. Anytime acceleration is opposite velocity, you get a deceleration. Okay, so that sort of relates to these problems, right? When this car is going around the track, the motion, as I think we even observed the other day, is not uniform circular motion. It's non-uniform circular motion. It's hard to tell when it goes fast, but if I go so it just barely makes it around, you might be able to see that it speeds up as it goes down and slows down as it goes up. And that kind of makes sense. If we imagine drawing a free body diagram, I'm sorry, I should unshare for Hamangi. If we imagine drawing the free body diagram as this is coming down like that, looks like it's speeding up. So here is the mass on the string. And if I draw the forces that are on it, the string tension is in this direction. The weight force is straight down. So if I draw the net force on it, using our old parallelogram rule, maybe this is the direction of F net. I'm just kind of making it up, but it sort of points in that direction. And that means the acceleration overall has to point in that direction. So it has For whatever speed it's going at, it has the correct v squared over r acceleration component in this direction, but it's also going to have an acceleration component along that direction too. Now, that didn't affect our calculations that we had in the previous slide here because, well, first of all, we were only using F net equals ma components along the radial direction. So who cares about the tangential component of acceleration? But as you might imagine, at least at the top and at the bottom, it's also true that none of the forces, you know, the tension at the bottom is pointing up and the weight force is pointing down. So none of the forces at the very top or at the very bottom point along the direction of motion, but they all point in the radial direction. So it didn't affect our calculations there. So that's worth remembering, just that when you're speeding up or slowing down along a circle, the radial component of the acceleration has the same formula. And in addition, you have some tangential acceleration, which represents the rate at which the speed of the object is changing. We could call it the tangential velocity. And sometimes people will draw axes where instead of x and y, they call them r and t. So r is pointing inward along the radial direction and t is pointing along the tangential direction. And of course, those axes point in different directions as you move around the circle, but you might just use them at one point in the object's motion. Okay, one more reading response here. Let's see what it is. For the example in the book, I did not follow why a vertical circle would not have uniform circular motion. I think we talked about this. So despite both gravity and tension force being along the ball, when in a horizontal circle, are these forces still not acting upon the ball? Yes, but they're acting in different directions. You know, if I spin something in a horizontal circle, that's like the conical pendulum that we looked at yesterday. I got to keep remembering to share and unshare here. What? You can, and the person, you do have to enlarge it, I think, right? Because it focuses, yes, yeah. So maybe I'll let myself not do that, and whoever's at home, if you're having trouble with it, let me know. When I have a conical pendulum going like this is going in a horizontal circle, and then the tension at any point in time is tilted at an angle. The weight, of course, is always straight down. When it's going in a vertical circle, well, at least at the top and the bottom, you know, the tension might be down at the top and the weight force is down at the top. At the bottom, the tension is up and the weight force is down. So the forces really are in a different direction. Part of the reason I like to share and unshare the screen, even though it's kind of a pain for me, is that I'm recording these sessions and I do try to, you know, at least within a couple of days, post them on the website in case anybody wants to see them. And you'll see in the video whatever I have shared. So if I'm sharing the screen, you see my screen slides. If I'm unsharing the screen, then you see what's on the board, even though you can individually select those. I don't know if those are being used at all, but I think it's good practice for me because I have students who will be all online in next block, so I'm just trying to get used to having stuff. In fact, even one in China who's going to be asynchronously attending, so everything's got to kind of be posted on the web. All right, any questions on that before we go talk about gravity and do a bunch of examples on that? That's what you read about and watched last night. Okay. So as I said, I'm not going to go through the discussion of gravity, but I think it's very interesting. You know, most people don't know too much about early models of what the universe was, which back then wasn't too much bigger than Earth, of course. But I talked in there about flat Earth models with the firmament and the stars being sort of, you know, glowing points of light in the firmament and the Earth being flat. And, you know, some of the obvious features of it that make it appealing. And then later on, the observations by Aristotle and others with problems with that model, in that if you're thinking of this as your view of the universe, then you can imagine that no matter where you are on Earth, you should be able to see the same stars in the sky. But people had observed that when you go further south, you know, you're not thinking of Earth as a sphere, but you're traveling in a certain direction on the surface of this flat Earth. and you see new constellations appear that you never see in your hometown. That doesn't make any sense, at least from this naive picture here, if the Earth is flat. If I'm over here right by the edge, or right in the middle, or over on the far edge, I can see all of the same stars, and so that seemed to disagree with it. You know, there was also some Greek philosophy in it, and the sphere being the most perfect shape and things like that, that we wouldn't count as scientific necessarily, but lean toward a model of the Earth being round, still early on thought as the center of the universe. And I talked about in there Eratosthenes' very creative method for measuring the radius or size of the Earth. Yes, Jose. No, no, it's for your basic edification. And I just think this is such a neat method. You know, if you ask yourself, how as an ancient, even if you had the idea that the Earth is this huge ball, how would you measure the size of that ball? It's just sort of befuddling, and the creativity of using this deep well that goes straight down and this obelisk that goes straight up that are at widely separated distances, and then having someone measure out the distance in between and measuring the angle of the shadow of this obelisk when there's no shadow at the well in Syene, and from all that determining by a very simple calculation, once you've thought about it, what that angle alpha is there, and then using that to figure out what the radius of the Earth is. That's just kind of amazing. 200 BC. Okay, the next revolution was the sun-centered models, you know, Copernican kind of revolution, where people realized that the motions of the planets are actually kind of extremely complicated to figure out if you imagine the Earth's in the middle and the planets are moving around. The stars move very simply. They just seem to rotate around. That was the motivation for the firmament. But the planets have these crazy motions, and to explain them requires you really stand on your head to make a model where it makes sense. And Copernicus realized that if you put the sun, everything's simplified. We can still imagine the stars moving as a unit, you know, and Copernicus really, in this model, we should still think of a spherical firmament around the outside of all this. Yes, something, stellarum or something right there, something about the stars being the outermost sphere in this kind of model. So the stars are still these mysterious points of light that are spherical around everything, but this is the sun at the middle rather than Earth. Here's Earth right here. And then I talked about Kepler, and there's one thing I want to mention with Kepler's 3 laws of motion. They do follow from the Newton theory that we're going to discuss at great length, but there are some problems that can be simplified if you just start with one of Kepler's laws. So Kepler's laws were the orbits of planets around the sun are ellipses, not circles. And the sun is at one of the foci of the ellipse. Every ellipse has 2 foci, and I talked about that in the videos. Second law was that every planet sweeps out equal areas, where the area means make a sort of triangle with a curved edge to it. And that if you wait a certain amount of time at one time of year and you wait a certain amount of time at the other time, same amount of time at a different time of year, then the areas swept out are equal. And what that means is this planet has to be going much faster here and slower as it goes out here, because this dimension's bigger. So this dimension has to be smaller in an equal amount of time. So it tells you how the planets speed up and slow down as time goes on. The one I really wanted to mention here is the third law, which is sort of the most confusing perhaps, but there are places in the homework where you can do it with Newton's law of gravity, but your life will be a lot easier if you just go straight to Kepler's third law. Kepler's third law says, if A is the semi-major axis length, okay, so semi-major means the biggest dimension. So if we look at this purple ellipse here, the major axis is that longest distance across that cuts it in two. Semi-major means half of that. And as the ellipse becomes a circle, the semi-major axis becomes the radius of the circle. So we're going to specialize a lot to circular orbits in what we're doing here. And so you can think of A as the radius of the circle if something's on a circular orbit. And T is how long that planet takes to get around the sun. And so we've got various different planets. The ones that are farther out take much longer to go one revolution around the sun. The ones that are close in, like Mercury, and even Earth being fairly close in, have shorter periods. So when we say periods, that means the time for one complete oscillation or trip all the way around. And Kepler, by extensive planetary observations, was able to back out that if you took the cube of, let's imagine they're circles, the cube of the radius divided by the square of the period, that was the same number for every planet in the solar system. And you could calculate it just by noting what the radius and period was for one planet. So that's something in SI units, not a very interesting number. But what it means is, if I know, for example, the radius of Earth's orbit, and I know Earth's period, that's 1 year in non-SI units, right? And I can observe with my telescope what the period is for some planet that's far out, I can infer what the distance of that planet is from the sun by saying that A for the Earth cubed divided by T for the Earth squared has got to be equal to A for the other planet cubed divided by T for the other planet squared. And so keep that in mind when you're doing the homework. I think there might be one that I put in here. Well, in fact, there we go. I put these reminders in here so I don't pass by problems unwittingly. So I believe this is one that's almost like one from the homework for chapter 5, part 2. Period of the Earth around the sun is, and it sounds sort of strange, but astronomers have decided that the names of sun and Earth and Moon are proper names, so we're not going to put the in front of them anymore. I still have things where I have the in front of them, and most people usually say, people say Earth, but they usually say the sun, but astronomers have decided we're going to start saying sun rather than the sun. Period of Earth around sun is 1 year, of course, and its distance is 150 million kilometers. So let's pretend it's a circle, so that distance is constant as it goes around. An asteroid in a circular orbit around sun is at a distance of 335 million kilometers. What's the period for the asteroid's orbit? So see if you can calculate that. We'll see how to do this later on with Newton's law of gravitation, but it's quite a bit simpler if you start just with Kepler's third. Okay, I get 3.34 Earth years. So when we say years, that usually implies Earth years. 3.34 years. And the calculation is as simple as just saying, well, look, this constant c is the same for anything orbiting the sun. It doesn't even have to be in a circular orbit, but in this case, we're concerned with things that are essentially circular orbits. Earth's orbit is not perfectly circular, but it's not too far off. So the radius of Earth, this looks like the radius of Earth, but it's the the radius of the Earth's orbit, so the distance from Earth to Sun, cubed divided by the period of Earth squared is equal to a constant, but that's also the same constant for the asteroid. So you don't even need that constant in the middle. We can just set those things equal to each other, and this is what we're after. So it looks like the period of the asteroid, if I bring the square up there and then bring these things upside down on the other side, I'm going to have RA cubed times T Earth squared divided by R Earth cubed. And then we've got to square root it at the end, if I did that correctly. And notice it doesn't really, you could change everything to SI units, in which case you'd get seconds out at the end. But since I think it was given in millions of kilometers here, and years is what we know Earth's period for, if we put millions of kilometers and years on this side and put millions of kilometers for this, in other words, was it 335? Yes. If I put in just 150 for this, 335 for this, and 1 year for this, you'll find out that the millions of kilometers, which I left out, those units cancel anyways, because I have the same thing in the numerator and denominator. If I put them both in millions of kilometers, the units will cancel out there. This will be in units of years, so yeah, I get years squared, but then I square root it, so I get years back. So my answer would be directly in years. In a lot of cases, it's easier to switch to SI units, but this is one of those cases where everything kind of cancels out. So if you're using Kepler's third in this way, use whatever crazy units they put it in. They're probably going to ask in quest for the same units out, and they're trying to make your life easy. Questions on that one? That's just a side note that is sometimes useful. We can get this out of Newton's law of gravitation, but we'll see that. You want me to put the numbers in? Yeah, sure. Should I put them into this? Are you okay with this formula, or should we? Yeah, okay. So the asteroid's distance was 335 million kilometers, so 335 cubed. Earth's period around the sun is 1 year, so I'm going to put this in years. You know, maybe I could, the units associated with this are millions of kilometers cubed, but that's also going to appear in this one down in the denominator. Earth's distance is 150 million kilometers, and that's being cubed there. Yes, I forgot the square on there. Thank you. All right, let's go back to this, and then at the very end, it's very interesting. To me, it's interesting. In fact, we used to do a lab in Physics 110 long ago about Jupiter's moons and Galileo's observations about Jupiter. It's hard to think back now before the time when people had good telescopes, but Galileo was one of the first people to have really, really finely designed telescope, and he was able to observe not just Jupiter, but the cross-sectional kind of size in his optical eyepiece of Jupiter and the adjacent, what he at first thought were stars next to it, but then he saw them moving around kind of in a straight line, and he said, huh, maybe those are just like the moon goes around Earth. These are moons of Jupiter. And that was the beginning of the idea that there's not just one center of the universe, not just the sun or the Earth, but everything, you know, every planet, every star could potentially be some center that other things would orbit around. And that's kind of the beginning of the modern point of view, which starts a little bit before Newton. This Bruno, you know, didn't have as much evidence for it as Newton, but Newton was sort of synthesizing a lot of observations, both astronomical and the way things behave on Earth. But the modern point of view, or at least the Newtonian point of view, pre-Einstein point of view, is that we think of space as essentially an infinite container, and that space is the same everywhere. So if you're out in deep space where there's no air and there's no mass nearby, here just looks the same as over here. There's no way to tell the difference by doing any experiment. And it just keeps going on and on in all directions in a three-dimensional universe. And there is a gravitational force law, which we're going to discuss shortly, that tells how if you have two masses in the middle of that big container, what their force is on each other. And then F equals ma is going to determine how they move in response to that force. So that's going to explain how planets move. And as I said on the first day, this is a big deal because it unifies what for a long time was a totally separate area of study, the motion of the heavenly bodies, moon around Earth, but then also Earth around sun and all that, is saying that that's the same as this weirdly different feeling phenomenon of things falling at the surface of Earth. It just doesn't feel like the motion of the heavenly bodies, but Newton showed that the same kind of principle, this gravitational force law, and his second law of motion made them move in the same way. Okay, problem 4 doesn't necessarily have to do directly with that, but it was a problem I wanted us to think about because it also has to do with circular motion. Here we're talking about people standing on Earth, and so we know the gravitational force on them. It's just mg because they're at the surface of Earth. So we imagine someone standing at the equator, and someone, an evil being has a little dial where they can spin up the rotational speed of Earth. So someone's on the equator, they're in uniform circular motion. We're in uniform circular motion too, sort of at a higher latitude. So we're on a smaller circle. People at the equator are going on a bigger circle. So some, evil demon is slowly spinning it up and the Earth is going faster and faster just because it's easier to think about on the equator. The question is, at what rotational speed, I think I phrased it at, yes, well, I phrased it in terms of the period. How short would an Earth day have to be, you can put it in seconds or hours, for us to become weightless on the equator? That doesn't mean really weightless. Our weight when we're near Earth is always mg. But when weightless is in scare quotes like that, that means your apparent weight. You feel weightless, even though the Earth is still pulling on you with mg. So imagine, the beings speeding up more and more. You'll find out from your calculation, you feel lighter and lighter and lighter. Still have your same weight, but you feel lighter, and at some critical speed, you lose touch and you can just float an inch above Earth on the equator. How long would a day have to be? Yeah, that would be really cool, but too bad we can't do it. Probably wouldn't be so cool for the people who actually live on the equator and everything just goes to mayhem, but yeah. And then question B is, well, if we spin it even faster, maybe you could stand on the ceiling and feel normal. So what would be the period for a day there? So see if you can figure those out. If you're having trouble getting started, think of drawing a free body diagram for that person. Imagine they're not quite weightless yet, so the ground is still pushing up on their feet, up away from Earth's center. And then, of course, use F net equals ma with our v squared over r and the distance over time trick to convert that into the rotational, that v into expressed in terms of the period of the rotation of Earth, and solve for that period. And I should mention that at the very top of this worksheet is the radius of Earth on the very top of the first page, 6.37 times 10 to the 6th meters. Eratosthenes was the first one to get close to that number. I get 1.41 hours for A, if you convert to hours, and 0.995 hours for B. Okay, so let's think about a free body diagram for this person. I don't know what their mass is, but let's assume the person has a mass m. I'm just going to draw their free body diagram adjacent to it. And what forces are acting on the person? Well, they've got their weight force going towards the center of Earth. That's m times little g. And normally they would have an upward force from the surface of Earth on the bottom of their feet. But we're imagining we want to make that just go to 0, so you don't feel any pressure from the Earth under your feet. Essentially, you're in a very low Earth orbit around Earth, right? I'm sort of just floating above and orbiting Earth. Well, the Earth's rotating with me, but I'm still orbiting it. Okay, so this is my free body diagram for this critical speed. And as always, let's take plus x toward the center and do the sum of the force x components equals max. Left-hand side's easy. mg comes out with a plus sign. The right-hand side, oh, good thing I didn't know that m. It'll cancel out at this stage here, right? Times a. A is v squared over r. That, notice, the radius of the circle that I'm on is the radius of Earth. So in this case, that means the radius of the Earth. So that was the number that you needed that's on the front page there. All right, and the reason I put this as a placeholder parentheses is because I'm not after v, I'm after t. I could solve for v and then convert it to t. Yeah, let's just do that. Put a v in there. cancel the m's. That means v is equal to the square root of g times the radius of Earth. And once I've got that number, I know those two numbers, so I can calculate it in my calculator. I'm going to set this equal to the distance divided by time, and I can use any convenient distance divided by time. The time I'm interested in here is the period of rotation. We'll call that capital T always for the time it takes to go one complete revolution. And the corresponding distance that the person moves is 2 pi r, right? If t is the time for one rotation, they go exactly one circumference in that period of time. So 2 pi times the radius of their circle, and the radius of their circle is r Earth. So the idea is, I know this number. I'm looking at this equation right here. I know that number. We can calculate this number in our calculator, and so I can solve for t. Maybe multiply it up so it ends up in the numerator on both sides. And you get t is 1.41 hours, so many thousands of seconds, 5,066 seconds if you did it in seconds. Quite a bit faster, right? So instead of 24 hours, you're going around in 1.4 hours. Otherwise, you know, if it were close to 24 hours, people would feel almost weightless down on the equator. But your weight on a scale is going to be a little bit less than it at the equator than it is up at the North Pole, where you're not spinning in a big circle so much, but you're rather more, you know, the very North Pole, you're just doing this. You're not really moving in a big circle. All right, any questions on that before we do B? How would I change the work I've done up here if I wanted, rather than that, I imagine we're on the equator here, and I want to be able to stand with my feet up there, my head down, and feel completely normal, as if gravity's pulling in that direction. Now, we really know it's pulling in this direction. Earth is still down here. But I want to feel as if I'm being pushed up in that direction or pulled up in that direction, so that if I stood on a scale, the scale would read my normal weight in newtons. Or how does the free body diagram change? Okay, so the person, let me just redraw it. Here's the person in a building, and they've got their feet down there, right? Let me see. I've got a calculator here, so yeah. So the radius of Earth, I'm pulling off the front page here. That is 6.37 times 10 to the 6th. 6.37 times 10 to the 6th in SI units. This is 9.8. And this also is that. And so if I solve this first for t, right, what I could do is take the equation that I've sort of, you know, weirdly circled here, multiply both sides by t, that gets the t up there, and then divide by that square root of g times re. So I would get 2 pi re over the square root of g times re. Well, another way to think about doing equations like this is, you know, an equation means the two sides are exactly the same. There's no difference. And if they're exactly the same, then their reciprocals will be the same. So you're always welcome to just take two sides and say, I'm going to flip them over. This one becomes 1 over that, and this side gets the t in the numerator and the 2 pi r in the denominator. Just a different way. Or you could multiply both sides by the variable you want. Okay. Again, question, how do I alter my free body diagram? If we want this person to feel normal, in the previous problem, they had no force on their feet. What is the force we want from their feet upwards? What's the force? Yeah, normal. And the normal force up, right? Earth's pulling me down with force mg. I'm not accelerating, and therefore, yes. And so normally I feel a force, pressure on the bottom of my feet upwards. that balances out the Earth's gravitational force so I don't accelerate anywhere. So I'm used to feeling that. That force upward on me is mg. In this situation, I better have that force downward toward the center of Earth on my feet if I'm standing on the ceiling like that. And I still have the normal Earth's gravitational force going down. So let's just run the numbers through. Instead of mg, it just becomes 2mg, right? So down here, the only difference would be we have 2 mg's. And that means v gets a factor of 2 under the square root there. And so this just gets a 2. It gets divided by the square root of 2. So you have to spin it faster. We have that intuitive notion from the non-inertial reference frame that when you're spinning in a circle, you get thrown outward. So we want to get thrown outward so much that we can stand on the ceiling and feel normal. That's the idea. Other questions on that one? I like that problem just because it seems a little bit fun to think about, even though it's not really a practical kind of thing. All right, let me go back to sharing.
Still not getting T yet.
Are others getting T as one? So that's in hours, not in seconds. It's 5,000
This is in seconds?
5,000 and something seconds. If you put all SI units in, you should get 5,000 and something seconds. Where is it? And then the 0.995 hours is 3582, very close to 3,600, which is about an hour, or is an hour in seconds. Okay, so we did that. Then, this is sort of part 2, or at least the discussion of gravity is the beginning of part 2 of this chapter, where we want to, we're concerned with things going in circles. That's the point of this chapter. Well, if we consider moving along with Earth, so Earth appears fixed, the moon's orbit is approximately uniform circular motion. And same is true for Earth around the sun and a lot of other planets too. So it seems like things undergoing gravitational attraction with a planet or with sun is going to give us uniform circular motion. So let's investigate those. But all we know about gravity so far is that when you're near surface of Earth, the weight force is mg. But if I go significantly far away from Earth, we don't really know what to do. And this is about patching that up. So gravity is an attractive force. That means if you have two masses, and Newton's going to tell us a law that works for spherical masses, so it's good for, planets on planets or stars on planets, things that tend to be more or less spherical. It's complicated. There's a way to do it with calculus, but if you have a weird shaped body like me and a weird shaped body like this tripod here, you could calculate it if you had all the details of the exact shape of that, but it wouldn't be nearly as simple. It would be built up out of this law that Newton's giving us here, but we're just going to apply it to spherical things. Or we can also apply this law to any shaped body as long as it's being pulled by a huge sphere and it's really small compared to that sphere, because we can really treat it like a point mass, I'm not approximately a sphere, but compared to Earth's, this huge sphere down below me, I may as well just be a point mass if you pull back and look at it. So it doesn't really matter the shape of my body if the other one is a huge sphere. The law, so it's attractive. Of course, the force on the two bodies, this is Newton's third law. These force magnitudes have to be equal and opposite. So it's telling us the force on both of the bodies. It depends on the distance between the centers of the sphere. We're calling that r here. The masses of the bodies are m1 and m2. And g is a new constant of nature, the universal gravitational constant, called universal gravitation because it applies to every mass everywhere in the universe. It's not just something that's here on Earth, but it applies to everything in the universe. And g is 6.67 times 10 to the minus 11 in SI units. And I had when I was doing the video recording, I had those grayed out because you can kind of figure out what they are by looking at the force law. We know
Dr. Kelly, I can't hear you anymore.
Can you hear me now?
Yes, thank you.
What I'm going to do is just, because the audio is so much better when I use this wireless microphone, my batteries went dead, so I'm just going to change them. A little intermission here. I noticed in the original recordings that the audio was all muffled coming out of the webcam. So. I'm trying to be thrifty and actually use up as much of the batteries as I can, but then that means they go dead at some point. Okay, let me switch back to... Can you hear me now? Hamangi?
Yeah, sorry.
Okay,
Yes.
great. Back in business. Okay, let me go back to the slides. I forgot what I was saying, but in any case, I think I was saying the fact that this is really small. What that means is if G is really small, 10 to the minus 11, that's a decimal point with 10 zeros and then a 1, right, multiplied by 6. That's a tiny number. What that means in here is if I put all SI units in, if M is 1 kilogram, M2 is 1 kilogram, so I take 2 kilogram masses, separate them by a meter, the gravitational force between them would be 6.67 times 10 to the minus 11 newtons. That's tiny. You know, if I take a 1 kilogram mass here on Earth, its gravitational force from the Earth is 10 newtons. So this is 10 to the minus 11 newtons, 12 orders of magnitude smaller. So that's why even though everything is attracted to everything else in this room, in principle, in practice, we can completely ignore it. Otherwise, we'd all clump together in the middle of the room, right? And we wouldn't be able to do anything. But it really takes planetary size globs of mass before these forces get big enough to compete with the other forces that we're familiar with, which is contact forces. And you can really think of contact forces as ultimately being due to electrical forces, right? When my hand gets really close to this table, we all know my hand is made of molecules that have molecular, electron orbitals on the outside of them, right? And normally my hand overall has hardly zero charge on it. The same thing with the table. But when my hand gets close to the table, the electrons suddenly are much closer to the outer electrons and the protons are closer to the protons, and that electron repulsion makes it big. Well, the electric force is just inherently much stronger than this gravitational force. So electric forces kind of dominate here on Earth, whereas once you get to things that are the size of a planet or bigger, electric forces can cancel because things have positive and negative forces and they balance each other out and make them neutral. The Earth doesn't have much excess force of one sign or another. But there's only one variety of mass. All mass is positive. And so if you add more and more mass, it just gets bigger and bigger and bigger in terms of the force. Okay, so I did an introductory example. What force does Earth pull on Moon? Just throwing in the numbers. You can look these up in the back of your book, but it's 2 times 10 to the 20th newtons. You got to get used to putting big numbers in scientific notation in your calculator. So if you're not, most calculators have an exponentiation button. And so it's not worth putting something in your calculator that looks like 2.23 times 10 to the power 26. That's sort of cumbersome, especially if you have a negative exponent. You got to put a lot of times be very careful about it. But in your calculator, if I wanted to enter this in my TI calculator, I hit that button that says EE on it, and EE is short for times 10 to the power. So I just do 2.23 EE26, and that puts it in scientific notation. I believe you're also going to start entering some big numbers in Quest. And if I remember correctly, I wrote it in the syllabus, but there you use a lowercase e. So if you wanted to do 3 times 10 to the minus 7 in some units, you would write it as 3e minus 7 in your Quest answer, to put it in scientific notation. It's just not feasible when we're talking about 10 to the 26th to actually put all those zeros in. Okay. Let's go back here. I think, yes, there's a problem having to do with just this gravitational law. So let's try that one. Problem 5, a 65 kilogram person, so there's a lot of things being asked here, is in space station, and we're given the radius of the orbit. What's the distance of the space station from the center of Earth? So that's essentially the radius of its circular orbit. Space station stays in orbit without firing any thrusters. So in other words, it's just being pulled on by Earth as it's in this orbit, which is the normal way the space station works. What's the magnitude of the force on the person? What's the magnitude of the acceleration of the person? What's the speed of the person relative to Earth's center? See if you can figure out all of these things by using Newton's universal law of gravitation, which is right here. And that capital G is also on the front page if you need it. Mass of Earth is on the front page as well. And F net equals ma. That's all you really need to do to answer these 4 questions. The last one refers to the orbital period, but you can use the old distance over time trick with 2 pi r to figure out what that orbital period is. Anybody need help with their calculator? Or getting started on A or B?
Took the radius of a 2πr to find the circumference and then divided that by the speed.
But you're not using the radius of Earth, are you? Because this person is not on Earth, they're farther away, so you need, yeah. Okay, let's go through these. I know not all of you are through all of them, but some of you are starting to get done. In A, we're just going to plug into Newton's law of universal gravitation. So that's G, the first mass, the second mass, the product of those masses divided by the square of the radius, distance between the two. So in this case, we're told how far the person is from the center of Earth, 6.7 million meters. G is 6.67 times 10 to the minus 11, so I've got to put that in. The mass of the person in SI units is 65. The mass of Earth, 5.97 times 10 to the 24th. That's on the front of the worksheet in kilograms. Divided by the distance between the person and the center of the Earth. Remember, we always measure, if we have a spherical body, we measure to the center of that spherical body. When there's something tiny like a person, we can just pretend they're a point mass, ignore like the shape of the mass and pretend they're, compared to the Earth, they're effectively a point. So we, you know, the center of that sphere is just wherever the point is. And in this case, it's 6.7 million, 6.7 times 10 to the 6th meters away, and that R is getting squared. So that's the distance from the person to the center of Earth. And apparently when you put all that in, you get 577 newtons, which is, you know, this person's substantially, if you compare this to the radius of Earth, it's quite a bit bigger. The normal weight of this person would be what? Well, G is about 10, 9.8, right? So if I do M times G, we would expect something very close to 650 newtons. It's a little bit less of a force when you're that far away from Earth in this space station orbit. I can't remember if I looked up, I think I did look up the actual, you know, rough orbital radius of the space station. What is the magnitude of the acceleration of the person? Well, then I've got to do a free body diagram, right? This person Of course, they're inside the space station, but the person themselves is, yippee, is going in a circle, right? And that circle has radius 6.7 times 10 to the 6th. And so let me do a free body diagram for that person. 65 kilogram person. There's only one force on the person, and that's that gravitational force that we just calculated, 577 Newton. So if I do, let's take plus x towards the center of Earth, as I like to do when we're in circular motion. The sum of the force x components equals max. Sum of the force x components, there's only one force on this person, and it's the one we just calculated. Comes in with a plus sign for my chosen x direction. And that's equal to the mass of the thing in the free body diagram times the acceleration. And in this case, this person's in uniform circular motion. So that is, well, we want to know, yeah, I forgot what we were asked for here. We're asked for the magnitude of the acceleration. So we'll just call that A and solve for it. 8.87 meters per second squared. Again, we're seeing the sign that we're a little bit farther away from Earth, right? On the surface of Earth, we would expect 9.8 if something's orbiting right above the surface of Earth, if they could do that. Air resistance makes that kind of impossible unless the air is moving with you, like if the Earth's rotating really fast. So compared to 9.8, free fall acceleration magnitude up that high is 8.87 if you release something from rest. C, once I know that acceleration, how do I figure out V, the speed that this person has to be going at? If they're going too fast, they wouldn't be on a circular orbit of that radius. So how fast do they have to be going? Yeah, now I've got A, whatever A is, our number was 8.87. That's coming from V squared over R, where R is, what was it, 6.7 million meters. So I can solve for V by taking a square root there. And then finally, once I have V, it's fast. Things that are in orbit are going really fast compared to, say, the center of Earth or something like that. 7,700 meters per second. 7,706 is equal, then I use the distance over time trick. The time is going to represent the time for one complete orbit, and the corresponding distance is 2 pi times the radius of the circle we're on, which is bigger than radius of Earth, and solve for t in that equation. So this is the kind of stuff we do for orbits. 77, no, so yes, should be 09. Were you asking what that is? Or why am I wondering about the 6? Yeah, I just misread it. Solve for t, and you get 1.52 hours is the period. I can't remember, when you're in the space station, there's a certain period of time they have to wait to see the same place on Earth be down below them when they're watching Earth. And it's pretty short. I think it's, I can't remember, but it's not that long. But it's also affected by the fact that the Earth is turning underneath them at the same time. So it's not like they just have to wait one period. The Earth is turning underneath at the same time, so it's more complicated than that.
Are they going against the way the Earth is turning?
I don't know. I think they are, but maybe somebody in here knows. You could certainly orbit either way, and I don't know, practically speaking, what that is. It might be advantageous to go against the direction it's turning just so that you visit places on Earth more often. In case something goes wrong, you don't want to be hovering over some place where the power's gone out or something like that. I don't know. All right, let's go back to sharing the screen here and move on. So here's another interesting thing that's, to me, just as interesting as how Eratosthenes answered the question of what's the size of the Earth. You know, it's easy to say, oh, we looked it up in the back of the book, but At some point, there was no back of the book. It's the same way here. We're using the Earth's mass. How do we know the mass of Earth or any other planet, for example? We can't just go and weigh Jupiter. We can't weigh Earth. We can't take Earth and shake it and see how much inertia it has. So we need a more indirect method. And again, we're going to use Newton's laws to infer what it is. And the answer is to figure out the mass of an object, you have to watch something orbit it. And so here I'm going to watch the moon going around Earth. We make a free body diagram. It's not too complicated. There's only that gravitational force from Earth. And I'm setting aside the other question of how do I know how far it is from Earth to moon? Well, that used to be a more complicated question. Now there are more technological ways that we can figure that out with lasers very directly. But in any case, let's imagine we know the distance from Earth to moon. And do F net equals ma? On the left-hand side, there's only one force. It's Newton's universal law of gravitation. And REM is supposed to be the distance from the Earth to the moon. And on the right-hand side, we have mv squared over r, and a bunch of stuff cancels out. The mass of the moon cancels out. There's also a factor, and I don't know why I didn't show it on here. REM on this side cancels out with one of the factors of REM in the denominator on the other side. I could have canceled that out. But in any case, now let's refocus on what we're after. We're after the mass of Earth here. This is our V in parentheses, and V is, again, gotten by one circumference divided by the time it takes to go one time around. And we're talking about the moon going around Earth. That's about 27 days, 24 hours a day, 60 minutes an hour, 60 seconds a minute. So that's a lot of seconds, but it is whatever it is there. And then I can just calculate what the mass of Earth is, and you get something that from that is very close to the number in the back of the book. So that's an indirect way of measuring masses. So for example, by Galileo observing these moons going around Jupiter could infer, as long as you could have some way of knowing from the power of your telescope what the distance between the moon and Jupiter was, so what's the radius of the orbit that it's on, Galileo could infer what the mass of Jupiter was. So you can start making astronomical observations and determine what the masses of objects just by watching things go around it. Notice the key cancellation here is the fact that I don't need to know the mass of the moon to calculate the mass of the Earth because it cancels out. So I can watch something else go around it. I don't need to know anything about its mass. Whew, a lot of problems here. Let's look at problem 6. Here we're looking at Saturn, and one of its moons, Mimas, has an orbital radius of so many meters. What was that about? Oh, yes, on the very last problem, I changed a 1 to 3. It's not possible to have the number 1 there, and I didn't find out till I made my solution. So I changed it at the last minute to a 3, but I'd already printed them out for class. Yes, you didn't do that. Anyways, we're above on problem 6. We're given the radius of this circular orbit, and we're given the period of the circular orbit of Mimas around Saturn. Use Newton's version of Kepler's third law. What the heck does that mean? The reason I put this in here is because that same verbiage is used in one of the homework problems, and it's always sort of confusing. Newton's version of Kepler's third law is just this. It's F net equals ma along the radial direction, where for F net you use gm1 m2 over r squared, and for ma you use m times v squared over r. We'll show in just a second how that turns into Kepler's third law, but we're not there yet. So here we're trying to find the mass of Saturn by watching something going around it and knowing its radius and its period. I get 4.13 times 10 to the 26th kilograms. Notice again here that it's not even algebra, it's more like doing the arithmetic of keeping all these numbers straight in scientific notation. Sometimes can be one of the hard parts of the problem. And again, on the next exam, where big numbers like this will appear in a couple of locations, the most important thing for me is that I see you write down Fnet equals MA kind of thing that would get you the solution correctly. If you fumble on the way to that final answer, that's not a big deal. There's no physics contained in there, but writing down that something like this equation right here and then saying, oh God, I've got to solve for this and put all those in my calculator. All right, I'll try my best. Okay, so in this case, here's Mimas going around Saturn. There's only one force on it, and it's the gravitational force from Saturn. I'll just call that F. There's my free body diagram. As always, I'm going to take plus x going towards the center, so I don't have to put an extra minus sign in for A. And then F net x equals MAX. That's G times the mass of Mimas times the mass of Saturn divided by the distance between them squared, and that's 1.7 times 10 to the 8th meters. So there's gm1 m2 over r squared. That's equal to mv squared over r. M is the thing that's in the free body diagram. So that's the mass of Mimas. I'll write that as m subscript m times v squared over r. And again, I'm just going to put directly in v in terms of the distance over time trick. R is 1.7 times 10 to the 8th in SI units. So v we'll write as 2 pi r divided by the period, which is given as 23.3 hours, times 60 minutes per hour, times 60 seconds per minute. I'm just trying to put everything in an SI unit so that I know if I solve for the mass of Saturn, it's going to be in kilograms. The important thing, again, is that Mimas's mass, the thing that's orbiting, cancels out. So I don't need to know two masses in order to get the one mass. Otherwise, we'd be kind of stuck. And when you do that, plug in capital G that's on the first page, 6.67 times 10 to the minus 11. There's a lot of stuff going in there, but if I got 4.13 times 10 to the 26th. So that's kind of another amazing thing that we don't think about. But where do all these numbers come from, especially astronomers? It's just crazy how creative people get. But it's many, many years that people spend thinking about these kinds of things. Yes?
So they could have done all this math to figure that how
That's right. Post-Newton, people could have done this math.
How'd they find out the orbital radius of the moon and how long it took?
Well, how long it takes, we can observe the phases of the moon as it goes around. So that's pretty straightforward to do, to count in days, about 27 days. But the distance from Earth to the moon, I don't know off the top of my head how the ancients did it. Or when that was first discovered. The modern way of doing it, I think I said in the video, was when the astronauts visited the moon, they put something called a corner reflector on the moon. Corner reflector is 3 mirrors that are all perpendicular to each other. So it's like the corner of the room. So there's one down here, and one like this. And if you think of what happens when you shine a laser beam at a corner reflector, it undergoes 3 bounces and comes back in exactly the same direction it came in with. So if it's coming in at a certain angle, it goes bing, bing, bing off those 3 mirrors and goes back. Now it's displaced by a couple of inches. If you make those corners very precisely perpendicular, even though we shoot a laser beam from Earth and hit that corner reflector, it can still come back to the same laboratory. In other words, it's almost exactly parallel. You know, it's probably a little bit of error there. It depends on how precisely you can manufacture the corner reflector. So what they do is shoot a laser beam at this corner reflector that was left by the astronauts that visited the moon. Then we know the speed of light very precisely. So we can time how long it takes to go there and back, and we know the speed it's going at, so therefore we can infer the distance that it must have had to travel over, and that distance is twice the distance to the moon. Now, you know, there's a little bit of correction because it depends on where you are relative to the corner reflector, but that essentially gives it to you with great precision, at least for those two things, you know. If you were at the point where you're closest to the moon and the corner reflector was closest, you'd have to add on the radius of the Earth and the radius of the moon to get it exactly right. But still, those are kind of small corrections compared to the overall distance. But, you know, I suppose there's lots of people who know lots about how the ancients figured out things, or at least, you know, people who are not the ancients, but people around Newton's age, what they knew and what could be inferred. A lot of times it's surprising. Here's the next mystery. You know, you can keep digging for mysteries. We'll end here, but this last mystery we'll address is, well, wait a minute, where did capital G come from? And the answer is, well, Newton didn't know what capital G was. When we measure, you know, in most cases, it's too small of a force to measure in a laboratory what, you know, if I had a kilogram mass and a kilogram mass separated by a meter, the force should be capital G in SI units. It's too small to measure unless you're very creative. And so Newton didn't know what capital G was. He just thought it was a constant of proportionality, but nobody knew what it was. And therefore, the whole argument of how to calculate the mass of Earth depends on knowing what capital G is. Newton didn't know what it was, so he didn't know what the mass of the Earth was. He knew how to calculate it if he knew capital G. And the person who came up with the experimental method, where you do have to measure actually the tiny gravitational force between two objects that fit in the lab, was Cavendish. And the idea is we're going to take two lead balls, just because they're very dense material, and we have to measure the force between them. So here's what Cavendish did. He takes smaller lead balls, you know, maybe about an inch in diameter, two of them, puts them on a somewhat light rod, connects them like this, and suspends them from a light string. You know, certainly if you take a steel, you know, piece of steel wire, it's very strong tensile strength, so it can handle this. And you can make it so it's balanced, so the two are sitting on this rod and sort of balanced like this. And then, so you let the whole thing settle down. You have to be very careful about currents of air in the room because these things will get blown by currents. So you have to close off an enclosure and make sure that if it's oscillating, it settles down. And then once everything's settled down, you take two really large, maybe softball size lead masses, and put them a little bit to one side and the other side of these two masses. You close the door, you know, so that there's no more air currents in there, or at least they settle down. And what happens is those two little masses are attracted to the big masses, which are just being held in place, and they go toward it. Of course, they overshoot a little bit, and then they oscillate back, and the whole thing, with a very slow period, oscillates back and forth. But eventually it settles down, and the angle of this rod changes ever so slightly. And by knowing something about how hard it is to rotate this thread around the center, you can back out what the force must have been between those two masses. And from that, you know, if you know M1 and M2 and you know R and their spheres, that means we can calculate the force in terms, you know, if we measure the force, then we can back out what capital G is. And so Cavendish said, I have weighed the Earth by doing this, because essentially by measuring capital G, everybody knew from that you could get what the mass of the Earth is. Okay, boy. I think we just got like two more short little topics and two more questions on here. So this is more of a comment. I don't think I have a problem on it in here. In Newton's theory of gravitation, little g can now be calculated. Before, this was an experimental fact. Maybe we could make careful measurements of the rate at which this velocity increases and measure that 9.8. And to Galileo, it was sort of a miracle that everything accelerated at the same rate, 9.8 meters per second squared. In Newton's theory, the force on an object, which the old way of calculating was just mass times little g, can now be calculated directly from gm1m2 over r squared. If you're on the surface of the Earth, right, where little g equals 9.8 is appropriate, the distance your object is from the center of Earth is 1 radius of the Earth. So that's your r in that case. The mass of the object is what it is, but if I set the old way of calculating the force equal to the new way, the mass of the object cancels out. And from that, we get an expression for little g. Little g is capital G times the mass of Earth divided by the radius of Earth squared. And once I realize that, I realize I can calculate little g in other locations too, just by changing how I'm thinking about the calculation. For example, if we had done the same calculation on the moon's surface, we should replace the mass of Earth by the mass of moon. And we should replace the radius of Earth by the radius of the moon. And we get a number that's about 1/6 the size on the surface of the moon. We could also do it for the same mass, but further away. In other words, I want to find little g at 1 Earth radius above Earth's surface, so pretty far above Earth's surface. Well, the m hasn't changed. The mass of Earth is still down there, but now the r has changed from 1 Earth radius to 2 Earth radii. And you can calculate it there. And in fact, you can calculate what little g's strength is everywhere. And you find, of course, that it gets stronger and stronger as you get towards Earth. And so in Newton's theory, we think of little g as not just a value, but a vector. Its length is the gravitational free fall acceleration at that position in space. And the direction is the direction that if you released an object, you would see it start accelerating. So people call this a vector field. So in the region around Earth, of course, little g is big at the surface of Earth. It starts to get smaller. Things don't accelerate so fast when you get far away from Earth's surface. Okay, and there are a couple problems associated with that. I'm not going to talk about them here, but they just had to do with calculating little g, something similar to that. And finally, I think we've already kind of addressed this today, and this will inform those last two problems that we'll finish with. Two questions. If an object is going in a circular orbit, only one speed will do. If you're at a certain radius, there's only one speed that will allow you to orbit in a circle at that radius. And you can calculate what it is by the same stuff we've done before. Do a free body diagram. There's only one force on this object. F net equals ma, and a is v squared over r. The F is just gm1m2 over r squared. Solve for v, and there it is. So it depends on the mass of the thing you're orbiting and how far away you are, or in other words, what's the radius of the circle that you're traveling on with that object at the center. Similarly, oh, I forgot about this little side thing here. The question is, what would happen if an object were at this distance, but I reached out with my hand and I slowed it down a little bit? So it's on a circle, but I just slow it down a little bit. So it's going, 7,700 meters per second, and I slow it down to 7,000. It's at the same r, but I've just slowed it down in the tangential direction. What happens to it? And the answer is, well, it starts to fall towards Earth. It doesn't have enough speed to sort of keep going around. If I stopped it to rest, it would just fall straight towards the center burst. But if I slow it down a little bit, it keeps going forward, but at not such a great speed, and it starts to fall towards Earth. And then it gets closer to Earth, but as it's going closer to Earth, it starts going faster, and that causes it to get sort of flung back out. And it, just as Kepler told us, it goes along an elliptical orbit. That's the most general kind of orbit. And if you give it a little whack and make it go faster than it would need to go at that particular radius, it'll go in a different elliptical orbit. So we're just looking at one special case of the more general orbits. It's nice for us because we know what acceleration to use when it's in a circular orbit along the radial direction. So we're specializing to that. Okay. We've already done this. How much time does it take to orbit? All I do is replace that v with 2 pi r over t, where t represents the orbital period. And I can solve for t. But instead of solving for t, let me just humor me for a second. I'm going to solve for t squared. Doesn't seem like I'm quite done, but we want to
Dr.
say in terms
Kelly,
of...
looking at a PowerPoint presentation right now? 'Cause
Yes, I
can't-
am, and I'm sorry.
That's
I
okay.
must have forgotten to share the screen.
Thank you.
You're welcome. Now we're good?
Yes.
Okay. So I've done this and the stuff we've done several times with the 2 pi r over t and solve for t, well, actually solve for t squared. Why? Because this is how you get Kepler's third law from Newton's theory, F equals ma and gm1 over gm1 m2 over r squared. When I solve for t squared, I see t squared is proportional to r cubed, or if I inverted this equation, I could get r cubed over t squared would be g times m over 4 pi r squared. And that m, remember, is the mass of the thing that you're orbiting. So for Kepler, that would be like the mass of the sun. The radius, or semi-major axis length, cubed divided by the period of that object squared is equal to a bunch of constants put together that only depend on the mass of the thing that you're orbiting. For the solar system, that's the sun. So as long as you're all orbiting the same thing, r cubed over t squared is the same for all objects orbiting. That's not just true for circular orbits, which is how we derived it here, but it's also true for elliptical orbits, which isn't so obvious. Okay, I think we've done enough of this kind of stuff, so let's just go on to problems 7 and 8, the last two in this worksheet, and then we'll end it after we go over those together. 7, I think, has to do with something having to do with the period being given. We've already done a couple of these. 8 isn't so directly related to the period, but I put it in there for a different reason, to warn us about something that happens in the homework as well. So try 7 and 8. Okay, the diagram for 7 is on the board, and maybe you've heard of geosynchronous satellites. That means I want to be able to place a satellite somewhere where it's going to be able to see roughly the same spot on the ground as time goes on. So it's just sitting above the same location on the globe of Earth. And that means in this diagram, whatever rate Earth is rotating at, right, takes 20 out, whatever rate Earth is rotating around at it, and the amount of time it takes to go a quarter of a rotation, this satellite would have moved a quarter of a rotation, so it's above the same point on Earth. And to do that, you actually have to be pretty far away from Earth. It's much farther away than most low Earth orbit satellites, but you know, it's great if you want to spy on a certain location or something like that. So here is a 478 kilogram geosynchronous satellite at 2 times 10 to the 5th kilometers. I just changed that to meters, so 2 times 10 to the 8th meters. And we know the period is 24 hours for this satellite's motion because it's trying to stay above Earth, which rotates once every 24 hours. What's the force on the satellite? Well, I could, in this case, just use g times the mass of the satellite times mass of Earth over r squared, right? We have all of those things. But I could just as well, I think, to get this force magnitude, set it equal to m times v squared over r. So there's another option here. M is 478. Well, let me just write it out. This is sum of the force x components equals max that I'm filling in. The gravitational force that we're after is equal to the mass of the satellite times v squared over r. The period is 24 hours, 24 times 60 minutes per hour times 60 seconds per minute. And the distance it goes is 2 pi times 2.01 times 10 to the 8th meters. That's our v squared, and then we need v squared over r. It's a different way to calculate it than the gm1 m2 over r squared. This was just an example of using the period. I know we've done that several times. Any questions on that one? You know, I noticed in the number that I put in 2.01 times 10 to the 5th meters, and so I didn't convert it to meters, so my number is not a good number. But maybe you guys can vote. What'd you get for it? 508 newtons. Anybody else? 508 newtons? Okay. I guess in this case, there's no square root, so I'm just off by powers of 10. I have 0.508, and so I guess I have I have a factor of 10 to the 6th, and then divided by 10 cubed, so that makes sense. And the last one, all I wanted to point out is, here's a satellite moving in a circular orbit around Earth. We're given the period, which I changed my mind of to 3 hours. Determine the satellite's altitude above Earth. A lot of people don't notice that, but the altitude above Earth is not the radius of the circle that it's on, right? So we're first going to, in this problem, figure out what the radius of the orbit is. Here's Earth in problem 8. Here's the orbit. This is what we might call the altitude above Earth, right? This is radius of Earth. And this is what we might call the radius of the orbit, r. So I would suggest in doing this problem, again, same approach. We're doing the same thing over and over again, but that's part of the point of this problem solving, is to really get you feeling comfortable with this kind of setup. It's even simpler than kind of it was before we started talking about gravity, because there's only one force. So if I have this object up here, there's only one force on it. I'm going to take plus x going toward there, and I've got to plug in all the information. So the sum of the force x components is g times the mass of the satellite times the mass of Earth divided by r squared. R is the radius of the circle that you're moving on, right? Or it's the in this case, it's the distance from the object to the center of this large spherical mass. And that's not the radius of Earth. It's not the altitude either, but we'll get that at the end. So that should equal the mass of the object in the orbit times v squared over r. And in this case, we're given the period is 3 hours, so we better use my v squared over r is going to look like that. And here I'll use 2 pi r divided by 3 hours, which is 3 times 60 times 60 in SI units. And then I can cancel this mass. We weren't given the mass of the satellite. Run the numbers through and determine what r is. And I didn't actually write it down, but once you figure out what r is, you would say that number r is the radius of Earth plus that extra altitude. I'm just calling that h here. So I need to subtract the radius of Earth off from the radius of the orbit to get the altitude above Earth's surface. Usually that catches about a third of the class by surprise in the homework, so hopefully this helps to figure that out. In this one, my final answer was 4.19 times 10 to the 6th meters. But as usual, I will post my solutions. I have to change that one thing, but I'll scan it in right after class today and then post it on the website, as I've been doing for our other daily practice kind of stuff. Any more questions? That's chapter 5. In 2 days. I can't believe that. Well, have a wonderful weekend. I hope you get some free spare time this weekend. I've got my work cut out for me.